Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And hi to my dearest panelists, Prof. T.S. Dr. Rizal Effendi bin Muhammad Nasir, and also Dr. Fauzia binti Jerai. Thank you for your time in reviewing my final year project on utilizing waste cooking oil as fuel in CI engine. I am Muhammad Amirul Hafiz bin Zambri, responsible to optimize the arrangement of constant area rod fin type of heat recovery device to preheat the fuel blend, and I am under full supervision of Dr. Idris bin Sa'ad. Without further ado, for my introduction, the CI engine, or known as the compression ignition, is where the compressed air being mixed with the diesel fuel in the engine block to produce the performance to the engine. And at the higher pressure and the higher temperature in the engine block, the physical properties of the diesel fuel in terms of its density and viscosity become the most crucial concern in order to provide a proper injection of the amount of fuel to the engine by the fuel injection system. A high viscosity fuel may resulting in a poor atomization characteristics and a narrow spray angle by the injector, which may also harm to the injector system of the engine. So whereby in this study, I am proposing the waste cooking oil to be used as the alternative fuel, and due to the volatile crude oil price, many researches have been done to run the engines in other way, like hybrid and also biodiesel. And also the European Union once claims that almost 1 million tons of waste cooking oil produced annually across the globe. And shockingly, 40,000 tons of waste cooking oil generated in the Asian countries like China, Indonesia, and also Malaysia, whereby the abundance accessibility can be obtained in the food and beverage industry. So the utilization of waste cooking oil somehow has been discovered since decades ago. But however, from those experimental setup and study, they are more focusing on the accurate proportion ratio of the waste cooking oil in order to form biodiesel. And also complicated process is involved, like trans-esterification, in order to treat the quality of the waste cooking oil. And shown in the graph, in the scatter graph below, the lower section that had been circled in red, whereby the fossil diesel kinematic viscosity in centistokes, and also at the upper section of the scatter graph, whereby the waste cooking oil, pure waste cooking oil, kinematic viscosity in centistokes. So we can see that the proportion gaps between those oil source at the respective temperature are quite high. And also, due to that particular properties, in this study, I'm using the use of heat recovery device, which in order to elevate the temperature of the waste cooking oil at the highest rate, in order to reduce its viscosity and density. The idea is whereby at the elevated temperature, it may reduce the viscosity and density when the kinetic energy particles in the fluid can weaken the intermolecular forces, and which resulting in a lower density of the fluid, and also in a lower viscosity of the fluid itself. So in this study, the advantage is I am manipulating the fluid properties, and I am using the temperature variable to improve the behavior in order to be compatible as diesel fuel. So for the application, heat recovery device is actually play the same role as the heat exchanger in order to transfer heat between the working fluids through conduction between the device's material. So in this study, the HRD been designed with counterflow orientation to provide a better uniform temperature difference. And the hot gas, this is the benefits of my study, whereby I am using the recovered exhaust gas that been generated through the CI engine in order to supply the heat source for the system, and in order to form a simpler system. And also a lower development cost is required. And the deployment of constant area rod fins also been introduced in order to maximize the extended surface area. The idea will be more explained later. And the HRD is able to elevate the temperature of waste cooking oil at highest rate in order to preheat it to improve the fluid properties, and they're really ready to be channeled to the engine for combustion. So what is the theory behind the rod fins deployment in the heat recovery device design? So I'm looking at the Fourier's law of conduction, whereby the heat flux is dependent on the heat and the heat thermal conductivity of the material of the surface area of for the heat flow, and also the temperature difference at the respective plane which been observed. So when we are looking at the equation, there are three major variables. So in order to control the thermal conductivity, it's assumed to be require a higher cost in order for the material selection and the development cost. So by applying the engineering theory, engineering analogy, and also the engineering practice in designing the device, we can extend the surface area by deploying the rod fins in order to provide a larger surface area for the heat to flow, which resulting in a higher heat flux. So why we require a higher heat flux? The higher heat flux then will be explained in this simple general equation, whereby a higher heat flux may generate a higher heat transfer coefficient in the system, and eventually also can generate a higher temperature difference, whereby it can elevate the WCO temperature at the highest rate, and also higher amount of heat also able to be transferred to the fluids. So the problem identification is actually due to the high viscosity and high density of the waste cooking oil itself, where it able to damage the engine components due to its able to deposit the solid unburned particles, and resulting in higher emissions due to the incomplete combustion. And also the optimum viscosity need to be achieved to be compatible to the standard diesel fuel, like for ASTM D975, whereby the viscosity of the diesel has been set up at 1.2 centistokes up to 4.10 centistokes. So this is whereby the range of the viscosity that need to be achieved by the waste cooking oil. So the objective of my study is to monitor the highest temperature of waste cooking oil at the outlet temperature, which at the same time I can determine the ideal arrangement of rod fins in my HRD models. So moving on to part 2. On my methodology on my research, I'm using the ANSYS software for the simulation, and due to the MCO, I am not able to carry out the experimental setup, which I am really want to do. So however, I am proposing the simulation to proposing 5 models with different arrangement of rod fins of the heat recovery device, and I am considering the 3 major concerns, where are the outlet temperature of the WCO, the heat transfer coefficient generated, and also the temperature distribution throughout each system. And referring to the project flowchart as shown below, I am continuing designing the same model in order to achieve the higher outlet temperature of WCO towards the preceding models. So if the temperature that I have been determined is at the highest rate, so I can proceed with the simulation. So these are the steps on my methodology for the study. So these are the fixed geometrical dimensions of my heat recovery device model. So as shown below, as shown in the slide, is the base model for the heat recovery device, whereby I'm also adapting the dimensions that have been set up by my previous senior, which by Mr. Amir Hambali, in order to set as the benchmark to compare the result outcomes variations, and also to ensure the continuity of the study. So these are the proposed design models, whereby at model 1, I am proposing the deployment of the constant error rod fins with a number of 16 and mutual spacing of 20 millimeter. So with inline straight alignment. So whereby I am observing that an increment of 7.86% of the WCO outlet temperature compared to the base model can be obtained. So I proceed with the same orientation of inline alignment arrangement, but with a smaller mutual spacing of 10 millimeter and a higher density of constant error fins with 21 of them. So I'm observing there is also an increment of another 11.91% of the WCO at the outlet temperature compared to the base model. So I am improving my design by continue adapting the same orientation on model 3, but with a 15 millimeter mutual spacing. So I am given out with a lower percentage gaps between the model 2 with around 0.02% difference. So I am further proving my design through model 4 with a lower density of rod pins with only 14 of them and a larger mutual spacing with the same orientation. So I am observing that it is only 11.44% that the outlet temperature of whisk cooking oil can be achieved. So in model 5, I'm using another configuration as I have found the relation between the mutual spacing and also the density of the rod fins in the preceding models. So I'm continuing in model 5 with the zigzag configuration or staggered with a higher number of rod pins and also a smaller mutual spacing. Sorry. So for the meshing, to observe the result outcomes variations for each required variables and also to improve accuracy during the computation. So as you can see in figure 1 and figure 2, whereby the working fluid of the waste cooking oil been meshed thoroughly in the wall, the surface, and also the inlet and outlet in order to provide a more accurate computation. And also same goes to the hot CO2 gas that have been meshed at the surface and also in the inlet and outlet. So based on figure 4, whereby the overall diagram of the proposed HRD models been meshed. So I am, however, in meshing, I am improving some enhancement whereby I am adapting the inflation layer for the working fluids as they are the major concerns in this study. So I define it as the inflation layer due to the respective boundary layer region for every wall bounded flows. So more precise and accurate computation along the working fluid pathways can be generated through the computation phase. For the setup and calculation, I am using the K epsilon, the realizable setting, and also the enhanced wall treatment as in comparative to my previous senior study to ensure the result outcomes variations. So defining the properties, I am using the diesel liquid in the that have been available in the Fluent database. So for the waste cooking oil, I can the properties is unavailable, so I am representing as diesel. So the carbon dioxide is somehow available, and for the copper I am using is whereby the waste cooking oil pathways of the tank in order to its high thermal conductivity and also resist corrosion at high temperature. And for the steel, whereby I'm using for my material of the exhaust due to its its ability to resist high heat and a good appearance, and also in the automobile industry nowadays, the steel being the standard material selection for the exhaust, and it's proven for its performance. These are the fluid properties that have been defined in the setup and computation. So many of them I referred to the standard values for the specific capacity of the CO2, specific capacity of diesel, the mass flow rate of CO2 and mass flow rate of the diesel. These are the standard values, and also the 200 degrees Celsius of the CO2 been supplied, been defined in line with the previous study of referring to the Handbook of Air Pollution 1998 from a diesel cycle engine engine with no load. So with considered as the ideal cycle, which are the generated exhaust gas is ranging from 200 degrees Celsius and up to 300 degrees Celsius. So the I'm sorry. So for the WCO initially supplied at the 50 degrees Celsius. So these are the boundary conditions of my HRD device model. So whereby at model as shown in number 1, whereby the waste cooking oil is supplied, and at number 2, whereby it is flowed out to out from the system with a minimum thickness of the tube in order to maximize the heat conduction and also to reduce the heat loss to the surroundings, and also as shown in number 3, whereby the hot CO2 generated by the exhaust supplied at 200 degrees Celsius, and number 4, where the hot CO2 gas being released, and also a larger diameter of the exhaust is being designed in order to maximize the volume of the fluid to be supplied to the system in order to elevate the waste cooking oil at the highest rate. So the result are being represented through the surface integrals of the facets values as shown, and the simulation being considering the temperature distribution, the velocity streamline, and also the wall heat transfer coefficient as shown in the slide for every proposed HRD models. So for the results, these are the major concerns whereby the outlet temperature of each design and the heat transfer coefficient, whereby we can see that the model 2 having the highest elevated temperature with 184.24 degrees Celsius and the highest heat transfer coefficient generated among other models. So these are the base model, whereby it can only elevate up to 164.63 degrees Celsius, and also a low temperature distribution also can be seen in the design. So which resulting it to only elevate at that range of temperature. So in model 1, sorry, the temperature able to elevate up to 177.57 degrees Celsius, whereby through the deployment of the rod fins and a better temperature distribution also can be observed. So through model 2, whereby it is the highest one, the waste cooking oil can achieve up to 184.24 degrees Celsius, and the temperature distribution of the design somehow is constant and more uniform, so it can resist at the prolonged duration of the system to be generated. So these are this is the model 3, whereby the it also can be elevate up until 184.2 only compared to model 2. So model 4 also only 184.46 degree Celsius of the waste cooking oil due to the lower rod fins and also to the higher mutual spacing of each rod fins. And also for model 5, it able to elevate up to 184.21 only of the waste cooking oil outlet temperature. So for the findings, I am constructing the distinguish between the number of rod fins used in each design and towards the temperature of the waste cooking oil at the outlet. And also it can be seen that at model 2, the highest temperature is being elevated at 184.24, and the total number of rod fins is 21. And also at model 2, the highest heat transfer coefficient generated can be seen through this graph. So the effectiveness is further proven to the heat transfer calculation, and the Qmax being determined at 15.12 kilowatt, and also the heat transfer of each design being calculated and ratioed in terms of percentage to get the effectiveness of the design proposed. As we can see, the highest effectiveness is achieved by model 2 at 89.5% due to its high temperature difference that can elevate the waste cooking oil. So proven that the range of temperature as the conclusion can be proven due to the at the 180 degrees Celsius as shown in the diagram below, which are the oil sources that majorly consist in the waste cooking oil, which are canola oil, corn oil, olive oil, and also the safflower oil, where at the 180 degrees Celsius, it able to achieve at 3.44 centistokes, whereby it is compatible to the diesel viscosity, standard viscosity as defined in ASTM D975. So it can I can successfully say that my proposed models able to elevate at this range of temperature in order to be compatible as the diesel fuel. So for the conclusion further on model 2, I have proven the inline alignment of the constant area rod fins in the heat recovery device design, able to reduce the capital investment cost, able to save the irresponsible waste management, capable to adapt the applicable engineering concept in order to minimize the dependence on natural resources. And also we managed to figure out the alternative solution in order to manipulating the conventional dependence on the crude oil, and also to in this heat recovery device also able to reduce the operational cost, and also minimize the and also to as the wake up call practice to save the environment, and in line with the sustainable development goals 13 on climate action by providing a recycling energy generated in the industry especially. So a cyclic sustainability program can be adapted. Inshallah. So I'm done for that's all for my video presentation on my FYP. So I am thank you for my panelists, my dearest panelists, for giving the attention, and also I am thank you to my Dr. Idris bin Saad and TS Dr. Muhammad Hafiz bin Muhammad Noor, which have been fully giving the commitment in ensuring my project to be successful up to this stage. And also for my panelists, if you have any inquiries or any question, you may feel free to reach me at my personal number and also my personal Gmail. So that's all from me. Thank you. So I'm wishing to stay safe, and also Assalamualaikum warahmatullahi wabarakatuh. Assalamualaikum. Thank you.